Formar parte de nuestra comunidad significa tener el respaldo de otros profesionales, acceder a contenido exclusivo y participar en eventos extraordinarios. Soy Igna y te invito a unirte a la comunidad de Fractal, la mayor red de profesionales de mantenimiento en habla hispana, donde tendrás acceso gratuito a una amplia variedad de cursos y workshops con certificación, además de la oportunidad de participar en sorteos y concursos con grandes premios. Si aún no eres parte de la comunidad Fractal, únete ahora mismo haciendo clic en este enlace.
En Fractal, sabemos que cuando cuentas con todas las herramientas para realizar mejor tu trabajo, tu vida, dentro y fuera de él, se vuelve más fácil. Por eso creamos la plataforma de mantenimiento inteligente, para hacer que tus resultados en mantenimiento sean los mejores, previniendo accidentes laborales, adecuando los costes a las necesidades de tu empresa y generando un gran impacto positivo en el mundo. El mantenimiento es nuestra razón de ser y está presente en todos los aspectos de nuestras vidas. Por eso, trabajes o no en él, tú también formas parte. Vivimos en un mundo lleno de activos, ¿te has dado cuenta? Ofrecemos a los profesionales el mejor aprendizaje y contribuimos a su formación para que con el uso de las nuevas tecnologías ayuden a construir ese mundo que siempre quisimos tener. Las personas somos las responsables de crear una realidad mejor y ahora disponemos de la tecnología para hacerlo. En Fractal transformamos el mundo del mantenimiento en un sector sostenible, seguro y eficiente. Por ello te damos todas las herramientas para que el mantenimiento inteligente esté al alcance de todos.
Hola a todos, muy buenas tardes. Les saluda Igna Salazar y estoy aquí para darles la bienvenida a este workshop donde hoy estaremos hablando sobre el futuro del mantenimiento, dispositivos IoT, Machine Learning, Inteligencia Artificial. En esta sesión exploraremos la importancia de contar con datos sólidos para aprovechar el máximo avance tecnológico. Identificarás señales cruciales para determinar tu preparación y aprenderás estrategias efectivas para abordar la situación. No te pierdas esta oportunidad porque además todo esto lo haremos de la mano de un experto en mantenimiento, el señor James Reyes-Picknell, destacado exponente del mundo del mantenimiento, autor de libros bestseller, conferencista y especialista en aumentar la productividad y optimizar el valor de los activos físicos. Cofundador y presidente de Conscious Asset, un profesional con más de 40 años de experiencia en el mundo del mantenimiento, y nosotros desde Fractal nos sentimos realmente honrados de tenerlo aquí el día de hoy. Pero antes de comenzar, les quiero recordar que este es un espacio que hacemos gracias a la comunidad de Fractal, a la cual me encantaría que se unieran. Es sumamente fácil, solamente tienen que ingresar sus datos y ya tendrán acceso a material exclusivo. Aquí tenemos un código QR que pueden escanear y donde se van a poder registrar en nuestra comunidad. También estaremos compartiéndole el link dentro de pocos minutos. Se lo vamos a estar compartiendo a través del chat. Por otro lado, quiero aprovechar este momento. Mira, tenemos a todo el mundo muy activo saludándonos a través del chat. Tengo personas desde Rosario, Argentina, desde Talara, el norte de Perú, desde Nicaragua, desde México. Les damos la bienvenida a todos. Gracias por estar aquí, gracias por apoyar esta iniciativa. Y bueno, yo no quiero hacerlos esperar más y quiero darle la bienvenida a nuestro invitado de hoy, el señor Reyes-Picknell.
Now, I asked that question because not everybody is actually ready to use these technologies. So let's dig into, first of all, what the technologies are and what they can do for us. And then at the end of the presentation, I'll ask you the question again. Are you ready for it? This is a little bit about my background. I'm an engineer. I live in Canada, and my company, Conscious Asset, is located here in Canada. I'm the principal consultant. I graduated in 1977, so that was actually 2 years before the TCP/IP Internet Protocol was actually invented. So I predate the internet, believe it or not. So technology in my lifetime has changed dramatically over those years. I've got a fairly long career, all of it in maintenance and asset management and reliability. I worked in the Navy as a ship's engineer. I've worked in petrochemicals, shipbuilding, aerospace, and I've done work in consulting since the mid 1990s. I worked at Coopers & Lybrand, Price Waterhouse Coopers, and IBM before I started my own firm here in 2004. All of it is specialized in reliability and maintenance management. So I've published a number of books, magazine articles, blog articles on our website, and I've spoken at a number of conferences, including Latin America, in Santiago, Monterrey, and this year in Colombia. First of all, let's look at the industrial Internet of Things. Now, I've called it IoT here, just Internet of Things, because it has both industrial and consumer applications. In the consumer world, which we're all familiar with, you have your phones, data, text, and communication. We've got our televisions, which are basically monitors, where we can live stream movies and entertainment. We can watch the news or our favorite television shows. We have wearable devices. Some of us wear watches that keep track of our heart rate and the number of steps we take and so on. We can actually do navigation using GPS, using our phones or our watches. In our homes, we have the Internet of Things. We have, if you've got a more modern appliance like a refrigerator or some stoves and microwaves, for example, some of those are actually connected to the internet and send condition status back to the manufacturer, so they can actually identify problems in your appliances. In my home, I have, for example, a thermostat that controls the temperature, whether it's heating or cooling, and it actually is connected to the internet, tells me what the weather is outside and what my temperature and humidity and so on are inside the house. I can have home monitoring systems for security, emergency notifications to emergency services and first responders, or even have remote viewing. I can have cameras in my garage or at my porch so I can see who's coming to the door. I can automate lights, climate itself. So if I go away on vacation, the house isn't overheated in the winter when I'm away, but it looks like it's lived in. I can actually open the doors remotely using access control. So these are all Internet of Things applications in the consumer world. Now, if we go to the industrial world, we've also got all of those, of course, plus machine monitoring for conditions and performance. We can actually turn equipment on and off remotely using our devices. I know people that can monitor their equipment performance on their phone from home while they're looking at the equipment in their factories. In our cities, we have traffic control with cameras and sensors in the roads. We have cameras for security and crime detection. We have transportation systems where location of buses, for example, are shown and can be displayed at a bus stop so you know when your bus is going to show up. We can actually control the movement of those buses by sending signals to the drivers. And of course, they're all trying to stick to a schedule, but as we all know, traffic gets in the way. Other industrial operations include healthcare, condition monitoring of both people and equipment, and the buildings, of course, used in the healthcare profession. Information management and sharing. We can share a great deal of information across the internet and various mobile and not mobile platforms. Paging of doctors, right? You don't dial a number anymore. You type it into a computer and say, I want this doctor, he gets a page. Security, control of the facilities, climate, lighting, security, and so forth. Monitoring of conditions within a facility, smoke, carbon monoxide gases, levels of lighting, whether or not spaces are occupied, controlling the actual access to the spaces. So there's a lot of applications that utilize the Internet of Things. So basically anything that we're controlling remotely somehow is making use of the Internet as a medium for transmitting signals back and forth, allowing us to control things. Now, the IIoT, the Industrial Internet of Things, is a collection of sensors, instruments, and autonomous devices, or actuators, if you will, that are connected through the internet to various industrial applications. They can be all over your plant. They can be all over mobile equipment. Now, the only difference between these new devices that we call IIoT devices and older condition monitoring sensors is that they typically contain programmed capabilities that the older sensors did not. So some of you may remember the days of online condition monitoring where we would have vibration sensors, thermal imaging, ultrasonics, and other sensors installed in our equipment and hardwired back to typically a box that collected the signals, and that would send signals on to your monitoring stations in the office somewhere. Well, the Internet of Things today is not much different from that, except that some of the computing capability is actually on the devices themselves. It's at the edge of the network, as they call it, and they refer to it as edge computing. Now, one of the reasons for that is that the volume of data, if you put a lot of devices in the field, the volume of data is absolutely huge. And it would overwhelm many networks in industrial environments. Some industrial environments don't even have networks, so that becomes another challenge to install. But the devices themselves will have a level of programming that actually learns what is the normal signal. And I'll talk a little bit more about that when we talk about machine learning. But it learns what's normal and detects when the signal goes outside of that normal range, and then it sends a signal off to warn you about it. So it doesn't send all the data to you all the time. It only sends the anomalies or the excursions from what it sees as normal. You can go in and query it. You can go in and see it in real time, but it doesn't normally send all that real-time data to you. It does get stored, so you can go in and analyze it later after an event has happened. Now, you can have many sensors in the field, and many of these sensors today now include multiple properties that they can sense. For example, vibration and temperature. I've seen humidity, relative humidity, all in the same sensor. So one sensor isn't necessarily just one signal. It may be multiple signals, each with its own computing capability at the edge. The internet connectivity allows you to combine information from those sensors in ways that might not have been so practical in the past. So for example, I can combine vibration and thermal imaging and oil condition information from sensors in the field with machine monitoring of, say, energy consumption, flow rates, pressures, temperatures in the product stream. So I can actually combine different signals in order to look at correlations among those signals to determine when I have a problem and what the possible causes of those problems might be. So what we have in this graphic is sort of the field devices, which are largely sensors. There may be transmitters in the field and repeaters as well in order to get the signal back. One of the characteristics of the industrial Internet of Things is that it needs a lot less wiring than the old field installed predictive maintenance or condition monitoring sensors used to require. One of the biggest costs of installing condition monitoring to operate on a continuous basis used to actually be the wiring. And of course, it had to be explosion proof depending on the environment. Today, these sensors are largely wireless, so they send the signal back to a transmitter, which basically agglomerates those signals together and sends it on for processing. So in the field, you got the sensors, you may have some transmitters. The signals themselves are not all the data isn't sent forward. It's the anomalies, as I mentioned earlier, and there will be some data saved for interrogation, perhaps 30 seconds prior to any event that occurs will be saved, and then that's continuously being deleted and refreshed. Those signals are then processed, and you'll typically have some diagnostic software that'll say, what does this signal actually mean to us? So the machine itself will start to interpret what the signal is telling us. Now, for maintenance, many of the signals we get in the field, we know what they should look like, and we know what the various patterns of bad situations look like already. For example, in vibrations, if I have a very high 1 times rotating speed vibration in the transverse direction, so perpendicular to the axis, I've probably got an unbalance going on. If I've got a high 2 times vibration in the axial direction, I probably have a misalignment. So there are patterns like that that we already know and can interpret, and those can be built right into the software. The machine will tell us what it thinks the problem is, and then pass that on to you as the user or the analyst, who's often an engineer or a well-trained technician, who then makes a decision. Do I agree with it or not? Now, he may go back and interrogate the live stream of data at the sensor. He may simply look at the historical data, that little window of data that's saved in the field for him to go back and look at. Or he may just say, yep, trust the machine, we've got a problem here, initiate a work order. So that's kind of how it's supposed to work. It's basically the same as condition monitoring has been for years. The big differences are that the internet is used for moving signals around. We've got computing at the edge, very large volumes of data, and an ability to process multiple streams of data and look for correlations that we couldn't do before. So when we're using the industrial Internet of Things, we've got to bear in mind that there could be potentially a very large number of sensors on a very large number of monitoring points. So take, for example, a mobile truck in a mining operation. You may have sensors, literally hundreds of sensors installed on the machine itself. They're all sending signals back to basically a transmitter that is now connected via some sort of a network to a central monitoring station, which may or may not be at the site. In some mining operations, the monitoring of conditions is actually done remote from the operating site. So the sensors are on the machine, the signals are getting transmitted to a network in the operating location and then sent someplace else in the world. I know, for example, in Australia, you've got mines in the Pilbara region in the northern part of the country, and the monitoring is actually done in Perth, which is in the southern part of the country, about 1,000 miles away. So that kind of thing is possible, which actually helps on the human resources side of things, because you don't need as many people in the remote operating location. And, for example, your engineers who are doing the monitoring, they could actually live in a city where they might prefer to be. Now, the data rates tend to be very, very fast. So we've got this edge computing, which limits the output of the devices to only the anomalies that it sees. So if everything's fine, it should be sending you very little signal at all. But when something goes wrong and it sees that as a variation from what it has learned to be the normal situation, then it tells you that there's a problem. You can go in and interrogate the data. So the guy sitting in Perth can check on the truck in the Pilbara region up in the northern part of his country. In that initial analysis coming from the devices, the machines themselves will interpret those for you. They'll tell you you have a high temperature on this cylinder. Perhaps you've got a problem with your fuel injectors. That kind of thing can be done by machines already using rules that we teach the computer. Okay, that's a rules-based learning, machine learning, which actually feeds the artificial intelligence, which is basically the thinking part of the computer that tells you what it thinks is going on. Some of these systems can actually learn. Many of these devices, when you first install them, go through a learning period, typically several days of gathering data and looking for what is that normal pattern of signal. If a failure occurs during that learning period, you have to restart the learning. All right, so the system may see a failure that occurs very early after you've installed and turned on the sensor. It may see a failure as being normal, which you don't want it to do. So if those failures occur, you have to remember that. Go back and tell the sensor, hey, we had a failure in there. Unlearn what you've just got there and start learning again. So that's something we have to manually control as it happens. The analytics themselves that come with this in the software are very, very powerful. We've got computing capabilities there that as individuals, as humans, we can't do manually very easily at all. But the outputs still require a human expert to look at them. Right? You can't just trust the machine on its own. We're not that far advanced yet. This diagram, which I've got the source of it there on machine learning, shows the different kinds of learning that happens. There's reinforced, there's supervised learning, and there's unsupervised learning. For example, in supervised learning, we use different analytical techniques. I'm not sure if my cursor shows on the screen here, but up at the upper right of your screen, you got supervised learning, and then it goes down to a little box that says regression. Well, you can actually teach the machines, that's the supervision part. We, the experts, tell the machine what's right and what's wrong by looking at what it is seeing and telling it that, okay, this combination of clouds means it's going to rain. If you see at the very bottom, it says estimating life expectancy. In the maintenance world, that's pretty important for us, because one of the first questions you'll ever get asked when you find a problem with condition monitoring is, how much longer can I run it? And of course, we can teach the machine to make a forecast. And there is a technique that I'll talk about a little bit later for doing that. So as you can see, there's different ways machines learn. The machine itself can pick up patterns, and we can tell it what the patterns mean. That reinforces, for example, the learning in the machine. That's one of the ways of teaching robots. We program them to move in a certain way. We observe the movement, and then we make corrections. And the machine itself learns the corrections. You don't have to do much programming to do that. The machine will change its own program. Unsupervised learning is where the computer basically does its own thing. It goes out and looks for things and tries to draw correlations. It's useful in marketing. You'll see targeted marketing, customer segmentation, and recommendation systems. Those are all results of unsupervised learning, where the computer is looking at the patterns of data that it sees coming in and the decisions that are being made, draws conclusions and correlations. It's also why sometimes on the computer, you'll see advertisements that you wonder, how did they know I was interested in that? Well, that's unsupervised learning, watching what you do on the computer and using that to feed back to the source of the information you're looking at now and saying, hey, pop up an ad that shows this guy a Coca-Cola or whatever it is. So there's different types of machine learning, and machine learning is basically the field of study that looks at statistics and how machines can actually interpret those statistics to tell us things. It is a form of teaching the machine, so it feeds artificial intelligence. Okay, so artificial intelligence effectively is the thinking part, and that's supposed to help us with decision making. And I'll show you some examples of what it can do here in a little bit. Machine learning itself is how AI learns. We can tell it what we want it to do. We can feed it patterns, for example. I described some vibration patterns earlier. We can tell the machine that, and then the machine will watch for it. Or we can let the machine find the patterns itself. There is a risk in that, though, that I'll talk about a little bit later in this presentation. Now, some of the applications that machine learning has been used for very successfully: speech recognition, pattern and object recognition. It can tell a ball from a box, a banana from an orange. Vision systems, I've seen those in use in robotics, where it can actually tell that the socket is attached to the nut and actually rotating. It can count numbers of rotations, things like that. I've seen that happen in robotic systems. We can use it in agricultural applications using satellite data to where should you plant, where is there enough moisture in the ground. Medical diagnostics, predictive analytics are used in medicine quite a bit. If I see these particular symptoms clustered together, here's what that means. We can actually use it also in generating text, so procedures and practices. And I've actually got an example in here a little bit later that I'll show you of using CHAT GPT, which is a generative AI, to actually generate some procedures. And I'll show you an example. It's actually, I did it myself for the first time as I was presenting this presentation, and I was actually quite surprised with how good a job it did. It's not perfect, but it's really good as a start. Computational statistics is used in machine learning, and data mining is also a related field of study where we use unsupervised learning, looking for patterns in large volumes of data. The challenge with that is the availability of large volumes of related data. The data scientists will tell you that the data doesn't necessarily have to be particularly structured, but in reality, if you want to get good results from it, it does help to have structured data there in the first place. Learning by machines is done much the way that much like a child will learn. And we've all seen children, and we've all been there ourselves, but when you're first learning, you're trying things out. You try something, you see if it works. If it doesn't, you don't do it again. You try something else. If it works, great. If not, you try something else, and you keep doing that. Now, the difference between a machine learning and a child learning is that a machine can just do it a lot faster, right? It does thousands of iterations a second, whereas the child might take years to do thousands of iterations. But we've all learned that same way, and it basically simulates that same type of learning in programming itself. It learns what didn't work, and it learns what does work. And we can reinforce that and accelerate it by providing input as the machine is learning. But here's an example of diagnostics using for predictive maintenance. Now, this one shows a car where you've got a number of sensors installed on the car, which you can see sticking out of the body of the car there. There is some collection of historical data, which could be on the vehicle or not. It usually is on the vehicle. And that communicates with a analytical system, which has some data storage, probably in the cloud. Our cars have communications out to the phone networks, the internet, depending on where it is, maybe a satellite even. I've driven a car in a remote location where I know there was definitely no phone coverage, but I did have satellite coverage. And believe it or not, the person at the OnStar Center actually could talk to me, even though I was in an area with absolutely zero phone coverage. And it was because I was using satellite communications. So you've got data, and with the data comes some predictive analytics and algorithms, just the same as in the factory that I described a little bit earlier. It will provide feedback to the driver, so it can tell you in the car that you have problems. It could go straight from the sensor to the alarm on the dashboard, or it could go to the screen that's in most cars nowadays and tell you what's going on, a little bit more detailed than the old-fashioned dashboard with just a few lights. And of course, it can also send that information to your dealer or your maintenance facility so that they know that there's something going on. And it allows them to now contact you. Hey, we just got a signal from your car saying that your oil level is low. You should bring the car in for an oil change. So that's an example of how the Internet of Things and artificial intelligence might work to monitor performance and condition in your automobile. Now let's look at AI and how it can help us in maintenance. Prognostics and diagnostics. So it's used much like in medicine to tell us what's wrong and tell us, in some cases, what we should do about it. So we use the signals that we get from our Internet of Things devices. We use the anomalies in the stream of data to tell us that we have a problem. We analyze the patterns in that data to tell us what we think is wrong in that equipment and system. And we've taught the system to do that. So a lot of mechanical problems will have very well-known patterns, as I described earlier with the vibration examples. So those can be observed and displayed very quickly for us to tell us, hey, you have an imbalance, you have a coupling problem, you have a misalignment, and so on. Process performance can also be used. Now, in many maintenance environments, traditionally, we didn't look at performance data. We looked at machine data, vibrations, oil levels, temperatures, things like that. But we can now blend in performance data, so energy consumption, flow rates. We can actually tell whether our machine, for example, if it's a pump, is operating on its pump curve at best efficiency or not. We can also use a combination of historical events and observation of the signals that occurred at the time of those events. We can correlate those and forecast remaining time to failure. So for example, there's a technique called proportional hazards modeling that is used for this, which takes historical events. Okay, I had a breakdown here in time. I've had a series of breakdowns, and here's the condition monitoring signals that I had around that time. And I look for correlation between which signal was actually going in an anomalous or a strange direction, and compare that with when the event occurred. And when I have a high correlation there, it tells me that that signal is important to tell me about that event coming up. And I can look at the time from when that signal started to go there until we had the event occur, and I can actually predict remaining life using that in the future. So when the signal goes to that point in the future, I now know how long I've got before that event is likely to occur. Very useful technique. We can also use artificial intelligence to help us with things like scheduling of our work by the basis of priority and criticality of the equipment. We can use it to schedule routing of where the technician needs to go in the field to take readings. We can use artificial intelligence to ask us questions that'll lead us to a work order priority, rather than just having us assign a priority, but ask us a few questions that'll let the machine, using our answers, and compare those to the rules that we've built into it, tell us what the priority should be. Another interesting thing we can do with AI is we can generate text. So CHAT GPT, I actually experimented with this and tried it, and it can actually produce procedures, standard operating practices, instructions, and so on. It's pretty remarkable what you can get from this, literally at your fingertips on a computer connected to the internet. My first exposure to this was with a client where we were working up some words in a strategy development session, and we were looking for the right wording to use in a vision statement. One of the individuals typed into Chat GPT, give me a vision statement for, and he described their scenario. It came back with a statement, and I looked at it and said, oh my gosh, that's something that I wrote years ago, and it was actually published in a book. So what's happened is these artificial intelligence have gone out and read information that's available online in various forms, and it basically brings that in and learns from it and then uses it. Now, depending on the size of your screen, this may or may not be readable, but I went to Chat GPT, which is available on the internet, and I said, tell me how to align a pump and motor using laser alignment tools. That's all I said. And it came up with the procedure that's on your screen there. Now, I won't read that in depth, but it actually wasn't a bad procedure. It said, prepare the work area, verify the base plate and foundation, mount the alignment tool, perform the rough alignment, start the laser alignment process, adjust the motor position. If you have to, adjust the pump position, verify the alignment, secure, lock it up, save the alignment data, and then do regular checks on it later. So that was an example of a Chat GPT produced procedure for doing a laser alignment. I did not measure how long it took to do this, but it was less than a second, I'm sure. It was very, very quick. After I typed in my request and hit enter, boom, up this came. Now, it's not perfect. It doesn't deal with a specific laser alignment tool, and there are different tools, so the way you use those needs to be covered, and that's not in here. It talks about adjusting the motor and the pump both. Well, chances are you're only going to want to adjust the motor. You're not likely to want to adjust the pump, simply because it's attached to the piping. The motor is only attached to the wiring. So there are a few things in here that may not be perfect for use directly in the field, but it's a pretty good start. And I thought to myself, because I'm working with some planners right now who have a lot of planning work to do, and I said, you need to describe exactly this kind of thing for your tradesmen. So why not use Chat GPT to produce a draft or a first cut at it, and it produces it very, very fast. Then you need your own knowledge, your own intelligence to go in and say, okay, I'm using this particular model of laser alignment tool. This is how I do it. I need to modify that part of this procedure that it's produced. Okay, we're never going to move the pump, so let's just take that piece out. We're only going to adjust at the motor end. So there's things like that that the planner would need to do with it, but this is a very good first start and probably saves him a lot of time. So it's a really good use of a tool that's readily available for free. It's kind of cool, but how many of us would be lazy? All right, now I personally wouldn't want to take that and put it on a work order and tell my tradesmen to use it, because it's missing those and has errors in those things that I just described. Somebody who's lazy might just copy and paste it into a work order book. All right, so we do need to make it specific to the application, right? Particularly in a job plan, which is the whole purpose of it, is to make the job easier for the tradesman. If you don't do it as a planner, then the tradesman himself has to do it. So the danger with it that I see is that having that available at your fingertips, and we all do as long as you got an internet connection, makes the job almost too easy to do. So if you're in a rush or you're lazy, or perhaps you're a planner that doesn't know all the details about that particular type of work, you might be inclined to just accept it. So my caution is that when we use AI generated content, we have to be very diligent in how we use it and applying our own expert knowledge to actually modify it and make it relative to our specific circumstances. So basically, use it as a start point, but don't trust it explicitly for everything that you might need it to do for you. We've got automated data gathering out there. One thing I've noticed is that data that's gathered by devices and machines is accurate. There's a lot of it and you can trust it. Manual data is a different story. It's got all kinds of errors in it. So automated data gathering is preferred. So I see this as a big advantage of the industrial Internet of Things. It basically collects data in the field automatically that in the past we may have had to collect manually by walking around. All right, so incredibly useful for condition monitoring, where condition monitoring will actually help us. Right, there are situations where condition monitoring isn't necessarily the best approach. Right, so there are examples, for example, of preventive activities where you know at a certain interval you have to change, say, liners in a mill, uh, where you know after a certain amount of hours of operation these things are going to be worn out. So there's no need to monitor condition. You're just going to stop it and change them. So let's not go overboard with it. And I think that's one danger with the IIoT is we could put sensors on pretty much anything, but are they actually going to be producing useful data for us? So we have to think a little bit about what we're going to put out there. But once it's there, it automates that data collection and the initial part of the analysis. We still, however, need somebody to think about what that analysis is telling us and make decisions. So do we still need manual data? Well, probably we do. Some types of data are almost exclusively manually collected and input. Now, maintainer and operators often conduct rounds in the plant. They go around and look at things. It's kind of a high touch, low tech type of approach to monitoring your systems and your equipment. Very useful for knowing what's going on in the plant. Now, if you're older school like I am, you want to get a feel for what's going on in the plant. I don't just trust the sensors. I've all too often found that sensors can be wrong. So I like to go out and actually see what's going on. And my human senses can verify sometimes what the gauges and the devices are telling me, and vice versa. But I can enhance those rounds with some automated data collection. So instead of actually writing readings on a clipboard or typing them into a tablet, I might be able to use automated data collection. So scanners or readers or near field communication devices to gather signals. I can see, and it's already happening in some environments, drones flying around with sensing devices or data collection devices that pick up signals from these Internet of Things devices that are out in the field. Very useful applications. I've seen them in use, for example, in power transmission lines, where they're literally flying the drone along the transmission line to observe condition of the lines, for example, for icing conditions that might take place in mountainous areas, or snow buildup, or wires that might actually have come down. It's a way of spotting that sort of thing. They can also pick up data that's collected and transmitted from the top of the tower itself, which perhaps isn't something that you can transmit any other way. So there's all these uses for data collection and transmission devices that are enabled today because of these devices. You still have to have a network somewhere, and in some applications there is no network, so you still have to rely on manual methods or storage at the site and then periodic collection of data as you go along. Work order data is pretty much always manual. It's gathered by manual methods. You know, how long did you work on something? What did you find? You're not going to get that from a sensor. What did you do? What parts did you use? Do you have any feedback for the planner? For example, if I used that alignment procedure that I got from Chat GPT in the field, my tradesman would probably tell you that, no, we don't ever adjust the pumps. We only adjust the motor. He would also probably tell you that procedure needs to be modified for use with the type of alignment equipment that he actually has in the field. So we could start generating those plans and some of the components of them with AI, but we still have that manual input needed from the expert, either the planner or the field or both. Now, is manual data actually useful? I've done a lot of work in studies of equipment and trends with equipment, and we've seen that it's not always the best data to use. Manual data is often missing parts or all of it. It It's often inaccurate. It may have been written down messy and transcribed incorrectly. If there's codes that have to be chosen from long lists, they always end up being wrong. People may not understand the codes or remember the codes. People get lazy and they don't want to scroll down a long list of codes. They just pick the top ones. Sometimes our work order data is lacking in specifics. All right, so you might have a work order that says go and check the pump, but it doesn't tell you what to check on the pump. Are you checking vibrations? Are you checking flow? Are you checking power consumption, or something else, right? And of course, that's now open to interpretation by the person in the field who may or may not do what you intended. A lot of times we don't even ask for the right inputs. All right. If you're trusting your CMMS, for example, to ask for input, be careful. They're programmed by programmers, not maintainers, and sometimes they're wrong. The manual data will relate to the machine and the work order, but it may be difficult to correlate it to specific failure modes. Right? Remember, the work order is a transactional data collection device, whereas the failure modes are actually events that you're trying to track, and they're not necessarily related one-to-one with the work order. And in fact, replacing parts doesn't necessarily tell you that the part had failed. Free text fields on work orders are very useful for the trades if they've got a good idea what you might be looking for. So you still need people in the field thinking and manually inputting data. That's not going to go away. Can we correlate manual data with automated data? Well, sometimes yes, sometimes no. Work order data is pretty much manual and it's transactional. Condition monitoring is a stream of signals, and it's not really transactional, but it leads to decisions that may lead to transactions. So that condition monitoring data can be correlated with event data, but not necessarily transactional data in work orders. Right? So we're now, if you think about it, your work order system, your condition monitoring data, and the event tracking, the failure tracking, might actually be in three totally different sets of data that need to be correlated now. Some data will correlate well, some data won't. Proportional hazards modeling, I mentioned it earlier, is used to correlate events with conditions to see which conditions most closely align or have the best correlation with the events that have occurred. And once you've established that, you can then watch for future conditions and forecast when events will take place, predict remaining useful life, for example. If you're going to use manual data, you can expect that cleaning up that data is going to be needed. Manual data is often highly flawed. The automated data is often very accurate. Now, in Franklin Covey's book, 7 Habits, habit number 2 is begin with the end in mind. All right, so when it comes to maintenance and reliability, what are the decisions that we need to make with all this data that we can collect and interpret? So we need to ask ourselves, what problems are we trying to solve? Now, a lot of the work in machine learning, artificial intelligence is done by data scientists and information technology technicians. So these are people who really understand computers, they really understand programming, but chances of them understanding maintenance are pretty low. They will point out to you that computer memory is cheap and it's abundant, and they are correct. So their answer to a data collection problem is just collect everything and then let the analytics determine what data is actually useful in there. And they'll look for correlations. Now, that's possible. It can be done. But do you need that data, all that data? All right. The volume of data that's out there in one particular machine that you might be monitoring. The volume of data for it might look like a lot, but for machine learning purposes, it's only one machine's data. You actually want data from multiple instances of the same type of machine in a very similar service in order to get any meaningful correlation that you might be able to use in forecasting problems and times to failure. And that requires sharing of data, typically with other sites and possibly even with other companies. Today, most companies are not willing to share a lot of that data. So for machine learning to really work well and feed the artificial intelligence algorithms, we probably need more data than we actually have in most applications. And I was at a conference just earlier this week where people were talking about this very problem. And even though they had terabytes of data from a national database here in Canada, they still found it was not enough for some of the algorithms. So don't put all your faith in it just yet. We're still going to need humans thinking to be involved. So when we're looking at the problems we're trying to solve, what machine problems are we dealing with, right? And we know what those are. We can forecast the kinds of failures that are going to occur, and we've done that in many cases. And if we've done something like reliability-centered maintenance, we've got a good idea what's going to happen. So we can use that to help tailor the data collection and the information gathering to feed what we need rather than just gather everything. Another question to ask ourselves is that if we find the solution to the problem, will we actually act on it? Now, I have seen several times where we don't. And there's some examples in our real life. Like, we all know that exercise is good for our health. But how many of us actually do regular exercise? We all know that diet has a big impact on our health. We are what we eat. How many of us go out and eat junk food every once in a while, or a lot? Now let's look at the data that we've got, the information we've got. How many of us get information from condition monitoring that tells us we have a problem and we failed to act on it? So that we did not take the necessary steps to actually correct the problem that we'd identified with our software, right? Now, if the answer is that you don't usually use that information, you're still at a very low level of maturity with condition monitoring, and you're probably not even aware of that. If you're aware that this can be a problem and you're really thinking about it, you're probably going to be using that information and learning as you go. If your environment today is very proactive, you're probably already doing this. You're already using the information that's available and acting on it in advance. That's how we avoid major consequences of failure. So we have to look at our own maturity in terms of our discipline to utilize the data from condition monitoring so that we can actually avoid the consequences that we're trying to avoid. Data mining. If I compare it to real mining. In a real mine, which I've got in the background of this picture, and that's a big iron mine in northern Canada, there's an awful lot of material there that we really don't want, right? We want the iron, we don't want all the overburden and the extra stuff that goes with it, right? It's all been put there by nature. We have to move all that waste and overburden away in order to get what we want. Now, with data mining, we do essentially the same thing. We get rid of a whole lot of information and data that we don't really need in order to find those few little nuggets that will satisfy our needs to solve certain problems. But if you think about it, Mother Nature built the real mine, we built the data mine. Do we really need to add all that data and collect it all? So when people are telling me that, storage is cheap and it's abundant, let's just save everything, I don't agree. I think we can be much smarter about that. If we use methods, and I mentioned reliability-centered maintenance as a good one, it'll tell us what problems we can expect and what we can do to monitor for them. We'll collect that information that's really, really needed. Proportional hazards modeling was a technique developed with the space shuttle to actually help minimize the number of data collection devices that had to go airborne in the actual shuttle. It helped keep the weight down by identifying which signals correlated to events and then getting rid of the sensors for that data that really didn't correlate well. Why record it if you're not going to actually need it? So we can be smarter. Something to think about when it comes to data and automating the look for correlation. Correlation between data is fairly well understood. If I've got this happening, this should happen. But they don't necessarily imply causation. They may, but they may not. And here's an example in the picture. If we've got hot, sunny weather, we can expect to see ice cream sales go up. We can also expect to see sunburns go up. So the correlation with causation is between the hot, sunny weather and the sales or the sunburns. But ice cream sales going up won't necessarily tell us that we can see an increase in sunburns or vice versa. All right, so we've got causation and correlation in the hot weather to the sales and the sunburns, but we have correlation between sales and sunburns, but no causation between the two. Okay, so we have to keep that in mind for our equipments when we're monitoring signals on them, that we may see correlations that are not necessarily indicating causes. And it's kind of important to realize whether they are or not before we start interpreting that information. Now, that's important because in data mining, we're going to find a lot of correlations. We may find positive ones where the trends go in the same directions. We may find negative trends where the trend is actually in the opposite direction. For example, reliability increasing can be associated with a decrease in safety incidents. And that would be a negative correlation, where there is actually a causation characteristic, but not necessarily in all cases where you find that. So we need to use our knowledge and experience, again, apply that expert knowledge to determine if causation is actually present. So big data, analytics, you hear all about that stuff. It's useful to find the correlations, but it may not always help you find causation. There are a number of tests you can do to determine whether there's correlation, statistical tests, and the data scientists are good at using those. But we still need our knowledge and our experience. We basically apply rules. So I'm going to end this presentation here by asking a question to you. Are you ready for the Internet of Things, for machine learning and its applications, and for the use of artificial intelligence? I will thank you right now for your participation in here, and I understand that we are going to be open for questions and answers.
James, first of all, I want to say thank you on behalf of Fractal for being here with us. Really, thank you very much.
You're quite welcome. It's been my pleasure.
Now we can start. We have some questions. We can start answering if you are okay with that.
Will do my best. There's a language barrier perhaps in the middle. I'm sure you can help me with that.
I will. So first of all, we want we have one question from Salvador Zuniaga. Él dice si podemos, que cómo superamos la resistencia al cambio cuando adoptamos estas tecnologías. So he asks, how can you overcome the resistance to change when you try to adopt these technologies?
Well, my experience is that the workforce these days is actually getting younger, not older. I'm perhaps an exception to that. And the younger people are coming in with a pretty high level of computer literacy and comfort with technology. So their resistance is actually quite low. The bigger resistance that I find in most companies these days, and it's not just with technology, but it's also with process changes and introduction of training programs, you name it. It actually comes from the middle management levels who, in my observation, tend to be responding to change from a point of fear. They're afraid of what it might do to them. And a lot of that is that they don't understand it. A good example of this, and I heard some interesting words from a colleague just the other day about machine learning. And people said, well, is machine learning, is artificial intelligence going to take over our job? Now, this was a consultant speaking, and he was afraid of it. And I told him, I said, you know, I don't really think so. Like I've played with it enough to realize that it's good, it's helpful, but it's not necessarily smart enough to do what we do as humans. And somebody else spoke up and said, no, machine learning won't take your job, but somebody else with machine learning will. You know, one way to get past resistance is to explain to them that okay, you're not going to get in the way of progress. Nobody has in the whole course of history. Don't believe for an instant that you're any different. You know, if they don't understand it, it needs to be explained. You know, like for example, this presentation itself. I'm hoping it explained a number of concepts that people may not really have a lot of understanding of yet. But it's not as scary and as threatening as people might think. And so knowledge is a big part of getting past resistance to change.
So that we still need human to do the work. So
Yep. Yeah. If you don't believe me, just ask Siri or whatever AI you've got on your computer at home to change your tires for you and see what happens.
no, that's really, really true. So we have another question. Carolina Rosal, ella pregunta si hay alguna forma de validar los resultados antes de implementar la inteligencia artificial o el machine learning. So, Carolina Rosal asks, is there a way to test some assets and validate the results before implementing machine learning and AI?
Sure, try it. You would actually have to install, on some test equipment. For example, if you want to use data collected in the field, you're going to have to install some IIoT devices to collect results, or just do a lot of manual data collection and then feed it into a database that your AI has access to so that it can read it. So yeah, you can do that. I would suggest to you that anybody selling this stuff these days has probably already done a lot of testing with it. So what I would be inclined to do in that situation is ask them to show you. They probably have implementations somewhere else that they could use as an example, and go do some industrial tourism and have them show you what they've done. I think that might work. To do that. But yeah, if you want to do it with your own equipment, you're going to have to go through the motions of installing it, which may entail installing a network if you don't already have it. It can be a bit of an effort. I remember doing some work on ships at one time. We were trying to actually just have the ship's data line up with the shore-based data, and we needed to use communications to do that because the ship is not always alongside connected to a wire. So we actually tested it using cell phones as a data communication device. So that was very primitive. That was quite a few years ago. But it worked. We were able to get the data to synchronize over the phone signal, which told us it will do it over a network or over a satellite signal if you want to go to the next level. So just think of a simple way to test what it is you want to do and then go and put it in place. But yeah, it's an experiment.
Okay, thank you very much, Jane. So I have a question by myself. Mm-hmm. So I want to, we know you are the author of 6 My Name books. So can you tell us briefly about them?
Sure. Well, there's 2 that are kind of the more well-known books. One of them is Uptime. I've actually got a copy of a few of them here. And I don't know if this shows, but that's Uptime. That's on maintenance management, and it speaks to a model of how to manage maintenance with 10 topics that all work together. So maintenance, materials, supply, information technology, KPIs, reliability-centered maintenance, how all these things work together to produce a good result in maintenance. Another book that I've done is Reliability-Centered Maintenance Re-Engineered. That one. And that one is co-authored with Jesus Safonte, who's originally from Puerto Rico. We wrote this book and it was published in 2017. Both Jesus and I use it to teach reliability-centered maintenance to our customers. I teach it in English. I've also got some online courses in English, French, Spanish, and Portuguese. But Jesus actually teaches it live in Spanish as well as English. He's of course bilingual. In fact, when we wrote the book, he wrote in he calls it English. I call it Spanglish, and I wrote in English, and we made the 2 work together. There's also a couple of other books, one on basic reliability management that's available on my website. Another one called Paying Your Way, which is about developing a business case for doing improvements in maintenance and reliability. And there's a couple of others on asset management there, one of which is very specific to where I live, not something you'd probably be interested in down in Latin America. So there's several books there, and a couple of others that I was involved with many years ago that would be pretty hard to find nowadays if you were looking for them. So quite a bit. If you go on my website, though, it's Conscious Asset, like the up above, only it's all one word, .com, and you'll find, I think it's knowledge, and then below that, you'll find books as a sub menu item.
Yes, actually, we share the website for everyone who want to know more about your books.
Thank you.
No, thank you very much, Jane. So we don't have more time, but I want to say thank you very much for being here. Like I said before, I hope to see you soon.
Well, you'll see me in Cartagena, Colombia, at the CMC conference.
I think so.
In July. I'm looking forward to that. Yes.
Yeah, we are going to be there. So
excellent.
Thank you very much, and see you soon. Bye-bye.
Okay, bye for now, Igni.